Okay, I'll start one. So, hi, that's me, but I have a very, very, very long career with Nokia. So I've had my hands in every protocol since GSM and 10 years with Trust and TPM. That's why my name is white. Okay. So what I'm doing this presentation, basically go through what we did and why we're in the state we are. Okay, so how do we get here? Well, I actually started about 10 years ago with the problem that how do we protect the telco cloud? There was this great idea that we're going to move all the 5G stuff into the cloud. Of course, nobody really quite understood what that was going to entail at the time. So we started off looking at things like Intel's open attestation, except back then it was called Mount Wilson and very, very much in beta stage. So the first challenge basically was how do we trust the machine, which is the basic, attestation protocols, grabbing quotes, etc. And we started looking at all the different places we could start testing stuff from. A few people point to the next picture. Over the years, we've looked at telco cloud, NFV. We did a lot of standardization on that, edge cloud, and then started to get much more into things like container security and IoT. That weird little box there actually is the world's most secure medical device. It is, it's actually a trusted ventilator, which we built about late 2019, just before COVID struck. Then we open sourced everything. Basically, you had a big mess of Raspberry Pis, Arduinos, everything with TPMs on there. The communications backplane wasn't hardware. We actually used the 5G network for this and did all sorts of clever stuff using 5G slicing. We built an attestation engine, which actually dates back about 10 years, to do very, very cool things. Not only could we go and attest the various different components on there, but we could even go and ask the 5G slice, go and attest yourself, and it would figure out how to go and attest all the stuff down there. So that's what we started off doing. And over the years, this ended up into asking two basic questions of anything, of any object or element of your system. First of all, is it attestable? Because, believe it or not, things need to be attestable before we can go and test them. And secondly, is it trustable? So, for example, Raspberry Pis are attestable. You can stick a TPM on it. They're not trustable. They could be made trustable with a little bit of hard work, but they're not really trustable. So the two questions of anything that you ask are they attestable? Are they trustable? We built something called the Nokia Attestation Engine, which apparently did all this for us. It's now called Jane, and it's owned by the University of Jyväskylä. It's all open source, but we ended up working initially with TPM 1.2, TPM 2, virtualized network functional VMs, containers, etc. So it was actually designed to be able to provide a consistent attestation interface to all these different objects. I actually have it as a demo. If anybody wants to see it, let's do it tomorrow over during the break. And then, of course, pretty much everything was based around the very, very traditional x86 UEFI chain of trust model. So that's where we came from. And of course, we ran lots of conferences, did lots of standardizations, and on a trip from Berlin, about 2017 on the flight back after a very, very bad conference, I wrote a file on my PC called what the XYZ am I doing? Replace XYZ with something much, much more explicit, which basically said that nobody understands this stuff. You cannot demonstrate security technologies to anybody and have them understand. So at this point, we decided to start turning things around and actually ask the question, how do we actually demonstrate security technologies? Because nobody was buying, hey, let's add attestation to TPM to the 5G network, or 4G network, or whatever it was. Doesn't happen. There needs to be some value for the customer. You need to be able to explain this. And more to the point, you need to be able to go and demonstrate it. And the other thing, of course, is just sticking a TPM in something isn't enough. You shouldn't be surprised at this, but I can show you systems where TPMs have been added and then managers walking off saying, hey, it's got TPM, it's trusted, it's secure, we don't have to worry about it. And if you're not laughing at that, I'm really worried at this stage because, yeah, I've got horror stories on that. Anyway, so yeah, if you just stick a TPM in it, it doesn't become magically secure, okay? So bear that in mind. So what we started doing was looking at much more interesting case studies for this. Okay, doing secure boot, measure boot, or anything like this is not particularly interesting. We've been doing that for a very long time, and it always ends up with the same question of so what. So to turn all this around, and this is a good way of thinking about any problem actually, is we started looking at some interesting case studies for mobile technologies. Railways was pretty big when we started this off in 2017. They have some particularly interesting security requirements. We did a lot of work with Rail Baltica, for example, who wish to run their entire signaling system over 5G, public 5G. And if you don't think there are some security issues in there, you're as crazy as they are. But anyway, it's a brilliant idea. We also then looked at probably railways. It's actually quite a hard industry to get into. First of all, they have an awful lot of very custom hardware. There are some very big players in there like Thales and so on. And secondly, the equipment is very expensive. Railway companies do not like you hacking their trains, but I can tell you some very interesting things you can do against railway networks that are particularly bad. They also have some very interesting requirements, especially in terms of latency. One of the requirements we've got is, if you want to go and test a computer on this train, you've got 500 milliseconds, which is a bit challenging when it would take something like 1500 to get a quote out of a TPM. So it's quite a difficult industry, but fun. We then also started looking at medical cases, which is also very interesting because the medical industry do not consider security as being an interesting property. They're much more interested in safety, and particularly come up with things like, it doesn't matter if the device is secure, you can just put a pillow over the patient's head. Yes, so VPN is not going to prevent you doing that. Industry 4, everyone got it, talking about that, IoT and edge. Basically, these are all the same problem. There is nothing special about Industry 4. There's nothing special about IoT and edge. It's basically, here are some sensors, here's some data processing, here's some more data processing, and you link them all together. The question then becomes, is what role does trusted and confidential computing play inside this? The nice thing about cases like railway and medical is that they give you a whole bunch of very interesting additional requirements on top. Latency, accuracy, resiliency, and so on. I quite like these cases are quite nice in the sense that when you do have a system that fails attestation, what do you do with it? You turn it off, reboot it, maybe reflash it again. That's something you cannot do with a life support system. People object to having their life support systems turned off to do a firmware update, especially if they're connected to them. So you get some very interesting cases like, hey, attestation of this device has failed. There's nothing I can do. That makes you start to think there are some very interesting things that come out of that. But we also are very interested into things such as, okay, if you have a device, a medical device with a TPM in it, you can do all the nice integrity stuff. What about the data coming out of that? Not just at the network level or the TLS level or anything like this, but the actual data itself. There is a huge amount of data coming out of this about the patient and so on. How can the TPM, can this attestation information be used to protect that data in some way? And we also turned that around to say, look, if you've got two devices that can be trusted, and you build a secure channel, and you can start doing interesting things with the information, the application layer that's being sent back and forth, then you can get some very interesting case studies. And we actually built this picture here. We actually built an intensive care ward in our lab at Nokia, or I built an intensive care ward in my lab at Nokia, I should say. And then we did a very interesting telemedicine demo where I was a few kilometers away, and then over the 5G network, and using some cool features there, we were able to control this device remotely and then do nice things such as swap sensors around and then watch the device go to safe mode and so on. Anyway, but what it turns out is that there's an awful lot of things in here that need testing, and everything has to be end-to-end. You can't just say that device is attested and leave it within a generally unattestable, untrustable system. Plus, of course, being a telco company, we had to demonstrate integration with the infrastructure, 5G, and now 6G. And then the other things that come after that is we have some very interesting failure modes, such as what happens if this part of the infrastructure fails? How do I keep the whole system up and running? So which over time led us to a big picture, and this is a big picture, which is grossly scaled down, is there's a whole bunch of concepts here that then end up being fitted in with each other. So down at the bottom is, how do we build our trusted computing base? We know how to do that. There's been quite a few good presentations here today on that. On the other hand, on the left-hand side, there's the whole supply chain. Where does all this information come from? Where do these devices come from? Where do the expected or golden or reference values come from? I know we've got things like the Linux LVMS service, the firmware update service, SigStore, etc. Just because data ends up in these services, or worse, hey, it's on a blockchain, it must be valid, doesn't mean that it's actually coming from a good place to start off with. SolarWinds saw that. They had their compilers were fine, yet the compilers were actually tampered with, etc. There's no mechanism to do that. And so that means that even if you have a nice, secure supply chain, there's still no guarantee that what you're getting is the thing that it really should claim to be, and so on. Within remote attestation, there are a lot of things. For example, what protocols do we have underneath? We build our own layer 7, layer 6 protocols and integrate that into our attestation engine. How do we manage elements in that? How do we manage the claims, the evidence? What are the trust decision mechanisms? And this is an interesting one. Just because your attested value matches doesn't necessarily mean your system is attested. What happens if a system suddenly becomes attested after spending the entire day being failing attestation, for example? So you need to take also the time characteristics into here. We can go through all of these things, how they integrate with things. But then above that, then you have all your interesting infrastructures. So, well, for me, this basically meant O-RAN, 6G, and so on. But there are places in there where attestation needs to fit. And then on top, of course, all the vertical areas with their things. On the right-hand side, digital forensics. So this has been rather a new area. There are 2 master's theses written on this, so not much. When something fails, you need to ask the question, why did it fail? Why did something fail its attestation? And it turns out that the root cause analysis trees that you might build for this are actually exceedingly complex. And it turned out for us that there were many cases that we never expected. So if a server reboots spontaneously and it comes back up and none of the PCRs have changed, well, that's good, isn't it? That's probably not a trust failure. For us, we had some of our server class machines. If they started up, you went to attest them, and you notice, for example, on the TPM quote, the reset value had increased by 3. So they'd had 3 reboots in a short period of time. Attested value is still the same, all the PCRs are still the same, signatures, everything. You still might want to fail that machine, because we actually discovered that, at least in the servers that we had, if you saw 3 reboots in succession, then this was probably likely that somebody had gone into the EVFI setup screen, and the machine had then gone through a very long, protracted power on self-test scenario where it actually gone and rebooted itself 3 times before properly rejoining the network. So we discovered a lot of weird little cases like this. That was quite interesting. It also turns out that if you have an attestation server that actually gathers all this information over time, then you can do some pretty interesting analytics over this. And we did have a case a few years ago that after an Ubuntu operating system updates do not alter the firmware. We saw PCR1 change on the TPMs of some of our laptops. That case is really interesting because it turns out that, of course, you can add code to the kernel that causes changes to UEFI configuration variables. So if you want to go and do some damage, you just add some code to the kernel to turn off the TPM in UEFI and persuade Linus Torvalds to accept it to do the next update of the Linux kernel. And there you are, you've turned off TPMs to reference machines. Anyway, we did find some interesting stuff there, and that's a long, more interesting story involving some agencies with 3 and 4 letters. And this stuff is completely incomplete. So we don't know what we should be doing with digital forensics in the long term. We know that it's going to happen. We know we have to build up response mechanisms. We know we have to build up orchestration mechanisms. It's just not there because it actually turned out that gathering the forensics and doing the analysis was such an interesting problem for us in the first place. The smaller picture that we keep coming across is that everyone has been talking about the chain of trust. You know, machine boots up, maybe you don't boot guard if you're lucky. You go through all the usual gathering PCR 0, 1, 2, 3 values, etc. up to runtime, and this forms a nice chain of trust that you collect from the TPM. We also have other chains of trust in the system. For example, if you have a container, its chain of trust is grounded into the supply chain. Similarly, if you have an enclave, how do you trust an enclave? Well, you need to know that, for example, it's a genuine Intel enclave for a start. It gets very interesting when you start having relationships like runs on, or runs in as I've written here. The container runs in an enclave. That enclave is part of the machine with the TPM, even though they're not linked. And in order to establish a trusted system, what we started looking at is how can we link these chains of trust together? Now, there are lots of linkages that make up a trusted system. For example, the links between the UEFI event log, IMA logs, TXT logs if you're using TXT, the quotes, the PCRs, the manufacturer of the TPM, that's another chain of trust. So linking all these chains of trust then gives you even more information about the state of the machine and need to be taken as a, effectively as a whole. So don't think that just testing, getting the values from the TPM is enough. You need to look at all these things, cross-reference them together. So over the years, we've come up with a number of questions about this. So what other structures exist? It can't just all be about enclaves and TPMs. Maybe a bit of supply chain. There's got to be more in there. There's a lot more interlinking structures. This is going to be, leads us then into what are the ontological models in here? How do all these things lead together? And that in turn leads us to an area that seems to be quite forgotten about these days, which is systems thinking. It's not about that single machine, or it's not about that single enclave and that single container. It's about a large ecosystem of things. If I do have a container, a trusted container running on an enclave on a machine somewhere, and that's communicating with another container somewhere, pretty much guaranteed. Parts of Open Radio Access Network talk with parts of the 5G network. That's a very interesting collaboration of things. Devices are spread across even geographically as well. All these things have an interaction with each other. If you have one piece of software talking to another piece of software, and one of them is trusted and one isn't, is the whole system trusted, etc.? How do you deal with less trusted things? And what kinds of trust do we want? What does the word trust mean in any of these systems? Does it mean that I've proved its identity and integrity? Malware can be trusted too. And rather sadly, I mean, I do remember one conversation with someone saying, secure boot is brilliant because we can't put malware on the machines. Well, I said, well, yeah, but we could sign the malware. But you can't sign malware, apparently. And there are people who believe this. They're called managers. So just be very, very aware of this. So you need to be very, very careful about this word trust, because I can have a machine riddled with malware. I can take the reference values from that machine, and then trust doesn't become this machine is going to do a big thing. I can now trust that this machine is going to do a bad thing. That's a very, very important thing to know, by the way. When you take this sort of systems approach and what this media trust means, you start to realize that trust isn't this binary yes or no. There are many, many shades of subjectiveness in here. So it's at this point in time, something might be more trusted than not. It's also time-based and so on. What are the mathematics of this? Does it integrate, differentiate over time? That's pretty cool to do. We've been looking at quantum trust, or at least I've been looking at quantum trust. So there are some papers out there that actually say, well, the trustworthiness of a system, or the trust in a system, is actually a superposition of it being trusted and not trusted, and some other things. Did somebody laugh then? Yeah, I guess think about that one for a while, because a system, you don't know what state it is in until you're tested. So yes, it is quantum. Anyway, the mathematics is really fun. That's all I'll say. So it will generate a lot of papers in that respect. Maybe I shouldn't say that. Then after a while, you get into risk and game theory. By the way, these diagrams here, we started thinking about also, because this word trustworthy comes up. If somebody talks to me about trustworthy AI once more, I'm going to scream. Apparently, I was actually in one meeting a few months back, and I said, well, how do you prove that this AI component is trustworthy? They said, it's simple. We'll get an AI to monitor it. I'm thinking, yeah, Alan Turing said something about that. I mean, it's like, oh God. Anyway, so every time you ask something, what does trustworthy mean? And we came up with some definitions. And by the way, this is category theory masquerading as description logic. So you have elements or objects in the system, and you can measure them in interesting ways. Those measurements are typically cryptographic hashes. Once you have all of those, you can go and perform an attestation, and you get a claim or a piece of evidence. Then you go and verify that evidence to give you a result, which is typically yes or no. And then after a while, you need to make a decision. And this is often forgotten. It doesn't matter how many results you have. You still need to decide over those results whether that system is trusted according to whatever criteria you had. So don't forget about the decision mechanism here. We then talked about, well, if you can get claims of it, then that means that thing is attestable. And if you can verify those claims, then that means it's trustworthy. Trustworthy meaning worthy of trust. So, if you say this thing is, trustworthy, then it just means that I can gather the information and I've got rules to decide whether it's trusted or not. And then quite simply, a trusted element is one where you've made a positive decision about it, which also then comes into the fact that can I make positive decisions about things that are inherently broken? But that's one for the philosophers. To take it further now, so what we're working on at the moment is Open Radio Access Network, and adding the word trustworthy in front of that, and then trying to answer what does trustworthy Open Radio Access Network mean. And there are some interesting things in here, and this starts to give you some idea of the complexity that builds around these systems. For example, the radio units, those big boxes that have been spreading COVID, your mobile phones connected. They're pretty powerful machines in their own right. I mean, they're typically based around ARM, I'm afraid, no RISC-V. But they're powerful enough to run the software either on bare metal or on containers and so on. That hardware needs to be trusted and identified for very, very good reason. This is part of critical infrastructure. You do not want your radio base stations to be tampered with. The software that's running on them, and we got cases here like multi-tenancy. So you might have, say, a Nokia base station that's running software from Huawei and Ericsson on top of it, and what can go wrong here? And that software there might be supporting multiple competing operators, Vodafone, Orange, and so on. And they all want to be sure that nobody's tampering with this stuff underneath. There was a case back in the 90s, I think it was, where British Airways had a mainframe, and they decided to sell off some of the computing power to an airline called Virgin. BA had the system administrators look at the Virgin databases, cancel people's flights on there and transfer them onto BA flights. Okay, so you don't want the same kind of thing happening with your base stations. Each of the base stations, of course, then talks to units called data units, and those to control units, etc. And that builds up each operator's radio access network. those containers there are probably running inside some telco cloud based on NFV. They're probably talking to various other containers providing 5G or 6G services and so on, which might then be provided by more operators. So we end up then getting the questions of, how do I trust the software that's running on that radio unit? Is it simply that that container is trusted and it's running in the enclave, or is the trust decision made out of the fact that in order to trust that container, I need to trust the enclave, and I need to trust the other software that's running there, I need to trust the radio unit, I need to trust all its connections, and so on and so on and so on. So these become very, very big, long, complex questions to answer. So our next steps, what are we actually working on? Ontologies mainly, that's what I think is quite interesting. What trust structures are there? You know, what kinds of cross-referencing do we need to do in order to make these decisions? What webs and multiple chains of trust are there? Better definitions of trusted. How do we get into the systems engineering from? Metrics for trust. Quantum trust decisions, or quantum decision theory. Okay, the maths is cool, okay? I'll just leave that. But quantum is, well, it gets you money at this moment. TPMs and enclaves aren't a full solution to this. Just because you have enclaves and TPMs doesn't mean that you're going to have a trusted system. They're a major part of it, and so on. Tooling is necessary. What we do need is a good attestation environment. So if you, Verizon, Keyline, and so there, okay. There is this one, it's called Jane. It was formerly Nokia Attestation Engine. It's a BSD licensed attestation engine. I'll give you a demo of that tomorrow if you want. There's a screenshot down there. Much more interesting cases from industry, medical defense, aerospace. ESA at the moment are talking about, or how they have research projects on putting TPMs in satellites. You know, what could you do with that? Think about that for a moment. Forensics, failure modes, responses, and so on. And then in blue text there's a whole bunch of master's theses that came out of Nokia. Borga Ravidas Turcanu looked at container trust. Victor Turcanu, one of my students many years ago, then started looking at the trusted build chain. Where did containers come from? Were they built in a trusted environment in the first place? And then you get the roots of trust of that. Ronnie Backlund looked at railway cases. He's now a railway cybersecurity expert in Finland. Kaisa Jatkala looked at blockchain, supply chain, and data trust. Tor Sommer, that some of you might know, he's been looking at enclaves, TPM, and containers and linking all these together in interesting ways. So he wrote also some extensions for Jane so when you launch a container using the edgeless container attestation or edgeless system, it would actually go and attest the machine, the container, the enclave, and link all three structures together, which is in quite an elegant way as well. Pekka Kura is looking at ORAN. David Mikulovsky is looking at the use of TPM in nuclear cases, because that's an industry where you do not want people tampering with your software for some reason. There are also cases, so I actually didn't know this, that in nuclear power plants, they have cameras installed by the International Atomic Energy Association. And these cameras send back live feeds to anybody who wants to view it. I assume you have to be an IEA member for a start. Think of it as Facebook for the, or Instagram for the nuclear industry. But it's there so you can monitor critical parts of the plant to make sure that nobody's doing anything bad, like, you know, here's a pile of plutonium, let's steal it. You've got cameras pointing at that. The data coming out of those cameras needs to be trusted. It needs to be notarized and so on. TPMs probably play a very, very good part in this at some point. Where's that data being processed, etc., and so on. So there are some interesting cases that come out of that, not just the standard, let's stick a whole bunch of sensors inside a nuclear reactor. And then Rosa Risto, Patrick Sundan from the University of Oulu, they looked at digital forensics and so on. So that's what we're doing. And I mean, the whole point of this presentation is really just to introduce this technology as something that sits in a much, much wider sort of environment and so on. Right, I'm going to shut up now, but if anybody would like to do a PhD in this area, I have PhDs open in these areas. Just give me a call and they'll see what I can do. But if you're interested in some pretty cool maths, quantum stuff looks interesting. Plus I have access to a quantum computer, which does not have a TPM at this point of view. Fine, but we can do something with that and so on. So I'll shut up now and any questions? Ready. Later.
Thank you. I wanted to ask, you mentioned that ontologies are required for formalization. How do you plan to use them, the ontologies?
The ontology. It's basically to define how all the individual structures fit together. So, for example, we know a TPM quote contains attestation data. It's got links to the PCRs and so on, but it's also got links out to the manufacturer. So if somebody comes to you and say, okay, how does my UEFI event log link with the TPM manufacturer, we would actually have a properly defined model on how all that fits together. So at one level, it's talking about basic data structures and how you operate across these data structures. So, some of the things that we saw this morning with ProVeric, you could actually write them. I don't know whether you're going to actually do a description module with ProVeric, but that's going to be fun for somebody who tries. But if you start taking this out in much larger things, so if you want to define policies, you need to answer the question, what do these policies operate over? And what different kinds of policies and how do these policies link together? So at one level, when we talk about ontologies in the wider sense, you can actually ground them down into sort of very precise descriptions of terminology and relationships between those terminologies. So that's what I'm aiming there. And then we can start building the operations over those, and then you get into all sorts of very interesting protocol things on that.
Thank you. We can talk more.
Yes. Yeah.
Thanks for the talk. There are some really good examples of things that we absolutely want to use attestation on, like doing the ones we started.
Defense. We're not allowed to say military. That's doing.
I said nuclear.
Oh, nuclear. Yeah, that's.
But sure.
That's
but one thing I've been thinking about basically since I started my PhD is like some things attestation can quite, there is a trade-off, right? One example that's missing here is Apple saying something along. They basically put attestation in their components for driving, so they want to replace it with a third party part. You can't do it because the TPM will not test it out, which is good for security, but kind of bad for freedom.
You get this quite a lot. I mean, TPM can be used for digital rights management, and digital rights management can be abused. But it's not a purely TPM thing. Any security technology. I mean, we've been doing DRM without TPM for a long time. So let's ban RSA because it can be used for DRM. Any technology can be misused. I mean, we had this argument when Microsoft added attestation to Windows 11 and demanded TPM. I think that's a good thing, not because I'm a Microsoft fan or like TPM, but it does take away a huge issue with certain kinds of attacks, certain kinds of failure scenarios, etc., that would occur. So I think that's a good thing. Now, if Microsoft decides to abuse that by saying you're going to use Microsoft authorized stuff because you need to match God knows what in your TPM, that will be a bad thing for the consumer. So, but then we get into something called societal effects. I'm not a cognitive science. I know some cognitive science people, they get very excited about this. What's the effect on the end user? Which, even though it's sort of fluffy and not formal, it's something you should always take, you should always think about that anyway. But yeah, you're right, it can be used in the long run.
So is this effectively user not part of your system thinking ontology?
It is very, very much, and that's actually how we ended up doing this case. And actually what came out of this, interestingly, was if we can build trusted medical hardware, we actually unlocked some very, very interesting use cases around telemedicine, and specifically control of the devices. So we had a project, back in 2019. You can guess why that ended in 2020. So they were a little bit busy at that time. Ironically, this is the stuff we wanted. But one thing that came out of that said, look, if we have a TPN, this isn't the only technology that can do this, but if we put a TPN into your medical device, we can do X, Y, and Z that you can't do now. Or you can do it now, but it's so damn dangerous. And they say, well, okay, so you've got a drug infusion pump, and we could load that with some drugs that only specific doctors can give. But then we can have those doctors, or one of those doctors, on call 200-300 kilometers away in a major hospital, and then we can give this to a patient. If that device is tampered with, we know. If we send a command to that device, both ends must be trusted. The device must know who sent it, vice versa. It unlocks some interesting use cases. And that's what we call the societal thing. And we use those use cases then as the demos. So in our medical use case, I've probably got video, this is probably a video on YouTube somewhere, but I'm not going to share the link. Unless you ask me very, very nicely for a bottle of whiskey or something. Actually showing what you can do with this. And so what actually that comes down to is, if you want to go and demonstrate a TPN, don't go to somebody and say, hey, look at this quote. Look, PCR4 change. You know, say, this is what I can do with it. This is what you will see as an end user. So that's where we came from there. So it's a way of thinking. That's it. But yeah, again, back to your original question here, DRM sucks. Okay.